So now I'm going to talk about a very interesting topic, that is the chaotic pendulum. I also like to call it as a nonlinear pendulum. So as we know that in the earlier lecture I talked about nonlinear systems, or the dynamics of nonlinear system. That dynamics of nonlinear systems, and these systems are found to be simple, complex and chaotic. They have different features, and chaotic, they are also found to be chaotic, means a new concept of chaos will emerge out. This is a new idea which will come out of the nonlinear dynamics, right? And similarly, if any differential equation is nonlinear, right, then this leads to a new concept of differential chaos. Right, this is a new idea will be merged out. Right. So to understand the idea of this nonlinear differential equation or the differential chaos, let us take an example of chaotic pendulum. Sometimes people call it as nonlinear pendulum. To give its idea, I will start with a very simple concept, that is the concept of simple pendulum. Means I will start with the simple pendulum and then switch over from here to the chaotic pendulum. So pendulum means a bob is attached vertically downward, and when some force is exerted on it, it will go like this. So different forces acts on it if it is a simple, right? So this is the angle, this is the angular displacement given to it, right? And it is the fixed at this end. So in this case, this is a torque, angular torque, and it is basically IA. Here A is the moment of inertia, and this A is the angular acceleration, right? So this tau is equal to IA, it is equal to minus mgl theta. Actually this is not theta, but actually this must be sine theta, but we have used here an approximation that theta is very small. That's why this sine theta is nearly equal to theta. That's what we are using here. And I can write down this equation also as I d square theta over dt square is equal to minus mgl theta. Or I can write down it as d square theta over dt square is equal to minus mg over I L theta, or sometimes it is written as minus omega naught square theta, right? So this is a differential equation of a simple pendulum. Here theta is a linear term, right? That's what we have to keep in mind. But let us take a case when theta is not small. When theta is not small, that means this sine theta is not nearly equal to theta, because sine theta, it can be written as theta minus theta cube over 3 factorial plus theta 5 over 5 factorial and so on. So that means when theta is sufficiently large, that means these terms cannot be ignored. So that means this equation is linear because we have ignored these terms because they are negligibly contributing. What if theta is not very small? That means they will also incorporate it into it. So that means this equation will become minus mgl this theta minus theta cube over 3 factorial plus theta 5 over 5 factorial and so on. So that means this will become a nonlinear terms because I have incorporated nonlinear terms here. So I call such a system as a nonlinear pendulum also. That's why I'm calling it as nonlinear pendulum, right? That's what we have to keep in mind. Now if it is a forced oscillator, let us take a case that when it is a forced, so that means this is simply mgl sine of theta divided by I. Sorry, I have missed I here. But if it is a forced oscillator and damping is also included, if damping is also included, then this equation will take a form that d square theta over dt square is equal to minus mgl over I sine theta minus beta over I d theta by dt. This is the damping term, and plus tau naught over I cos of omega t. This is the force which we have. This is a periodic force which we have applied, right? And in more simple form, this equation can also be written as d square theta by dt square minus mgl, sorry, not mgl, but it is minus omega naught square sine of theta minus alpha d theta over dt plus f of cos of omega t. So now this is a second order differential equation, and in this equation this term is not a linear term, this is a non-linear term. Earlier we have in lower classes you have studied that here is only theta term is sitting, but it is not theta, it is a sine theta here, and when I am incorporating sine theta here, so that means it is a non-linear differential equation. This makes it non-linear differential equation, right? And this equation is time dependent, and so thus we have I have talked about a chaotic pendulum, or I have talked about a differential equation for chaotic pendulum. So that's all for this lecture. So here I will talk about a very interesting concept, that is chaotic pendulum, where the nonlinear terms has been incorporated. So that's all for this lecture.